All right, today I want to look at a different example with related rates. This problem requires us to use a substitution of variables because basically we're going to have one too many variables in our equation. When we find the equation that relates the variables whose rate of changes we know and the rate of change we want, it's going to have an extra variable in it that we don't know anything about its rate of change. We can only have one unknown rate of change in these problems and be able to solve for it. So we're going to have to do something about that. So I'm going to read this problem. I suggest you maybe pause it and write this down in your notes so that way you can actually have that in your notes. But water runs into a conical tank at a rate of 9 cubic feet. It's cubic feet right there, feet cubed, per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? Okay, so you might want to pause, write this down. I'm going to go ahead and draw a picture. We want a conical tank with stands point down. Okay, I kind of feel like that cones is one of the better things that I can draw. So, just saying, I kind of like drawing cones myself. So it's a conical shaped tank with the point down. We've got water in it that's 6 feet deep, so I'm going to draw it about right there. But we got more water coming into it at 9 cubic feet per minute. That's going to be a rate of change for my volume. So that's a dV dt. That's the derivative of the volume with respect to time. Okay, because that's a volume change there. We're wanting to know how fast the water level is rising. So the water level rising, that's talking about a height. We know that the height of the entire cone is 10 feet. That's not changing. And we know the base radius up here at the top is going to be 5 feet. Now, the water level here, at this point, that changes over time. That's not staying the same because water's going into it. We know that water level is 6 feet. Okay, but that's changing, of course. But that's a height. This is a radius. Now, when we go to write our formula for the volume, we use the volume and we relate that to our height. We're wanting to know, since we're wanting to know how fast the water level is rising, we're wanting to know dH dt. That's our unknown. We're wanting to know that at h equals 6. So that's a value that we'll have to plug in after differentiating. We need a formula that relates our volume to our height, though. Well, volume is equal to 1/3 pi r squared h. That's our volume formula for a cone. Cones, pyramids, they have the same, all of the three-dimensional shapes. You're basically taking the area of the base times the height. Area of the base here is a circle, it's pi r squared, times the height. But with cones and pyramids, you do a 1/3 times that. That's how those formulas are changed, because you're shaving off so much of that volume there. So it's 1/3 times that. The issue here is I don't know. If I go to differentiate this implicitly, I have R and I have H. I don't know what how the radius is changing as the water level rises. I don't know dr dt. I only know dV dt and I want dH dt. There's too many variables here, so we need to use a substitution of variables to help us with this. Well, it just so happens that the geometry here works in our favor. If you're looking at this, the entire tank, if it was filled all the way to the top, the height would be 10 feet of the water, the radius would be 5 feet. That ratio is going to remain the same, or as you're going down, as you're decreasing or increasing that water level. So the ratio of 10 to 5 for the height to the radius That's proportional throughout this whole problem. So even here at 6 feet, the radius would then be 3 feet. In other words, 10 to 5, you see that it's half that. So that ratio of 10 to 5, that's the ratio of the height to the radius. We can solve this for the radius. So that's 10r, if we cross multiply, equals 5h. And if I divide by 10, I get r is equal to h divided by 2. That's important because that gives me the radius in terms of the height. I can now substitute that in, and I get 1/3 pi times h divided by 2, quantity squared, times h. That's 1/3 times pi times h squared over 4 times h. And h squared times h is going to give me h cubed. And 4 times 3 is 12, so that's 1/12 pi h cubed. That's my volume formula, only in terms of the height. Okay? So what we're going to do is we're going to differentiate this implicitly with respect to time on both sides of the equation. That's going to give me dv dt equals, we'll power rule this h cubed. So that 3 is going to come down. I'm going to have 3 over 3 times 1/12 is 3/12 pi h squared times dh dt. I know dv dt, I know what the height is now. Now that I've differentiated, I can plug in 6 feet for h. Because I've differentiated. After differentiation, remember that step from yesterday, after differentiation, then you can plug in quantities that change over time or depend upon time. So we know dVt is 9. 3 over 12, that's going to reduce to 1 over 4. Pi, we know 6, h is 6. The only thing we don't know in this equation is dH dt, but that's what we want. So we're going to solve for that. So this comes out to be 36. 6 squared is 36 times 1/4 is 9. So I get 9 equals 9 pi dH dt. And I divide by 9 pi. I'm going to get 9 divided by 9 pi equals dH dt, which simplifies to 1 over pi. That's going to be feet per minute. That's a height, so it's just feet, and that's per minute. That's the exact, you can get that as a decimal, but we would say that the water level is rising. When the water is 6 feet deep, the water level is rising by 1 over pi feet per minute. That's how you would write that out in context. Forgive me for not writing it in context here on the board, but that's how you would want to write that answer in context on a test. Okay? Questions? If you have any questions, you can let me know. I just said that by instinct there. Of course, you can't ask me questions right now because you're not here. So there's my lesson for today with this problem. I'm going to give you some problems today where you're going to have to use the substitution of variables. I'll also take questions today and tomorrow from the previous day's work. Thank you all.